Hi, this is a short video on AP Calculus BC integration strategies. We're going to cover some of the integral techniques that you see in Chapter 4 and Chapter 8 of the textbook and talk about how to distinguish between them. So first, you want to have a plan when you're approaching an integral. For students that sometimes say, I have no idea how to do this, it's because they don't have an idea in place of how to go about it. So this is how I do it. You might go through it in a different order or look for different things, but you want to start with some kind of plan. So my first step is it something I recognize? Meaning, is it something like the integral of sine, integral of tan, or some other form that you're just needing to memorize? So if it's a trig integral, you want to think about, is it one of the basic ones? If it's x to a power, we can do all those, or can I rewrite it as x to a power? So is it some form that I recognize? Second step is, can it be separated into different integrals? This is a trick you'll often see, something that doesn't look solvable, but if you separate it, suddenly they're easy integrals, two easy integrals versus one harder integral. Third thing I look for is u substitution. So I look for, is there a function and its derivative in the problem? And if there is that going to work out as far as is u in the right place and is du in the right place? If none of those work, I'm going to look for, is it rational? If it's a rational equation, it might be an inverse trig, like arctan. It might be completing the square, or it might be something where we can factor the denominator. And finally, is it integration by parts? So let's take a look at the first type. These are the forms that you should be able to recognize. So I have sine x here. Yeah, that's negative cosine. But basically all those trig functions you want to be able to recognize. Second one, is it x to some power? Remember, this could be just like a basic x squared, but square roots or cube roots, any kind of roots we can rewrite as x to a power. Anything like 1 over x squared we can write as x to the negative 2. So anything where x is a power, you want to be able to recognize. Constants, sometimes those throw us for a loop because we get so used to complicated questions. When we see just a number, we're like, huh. But yeah, constant, you're just putting an x with it. And then you want to be able to recognize things involving ln. So 1 over a quantity that's not squared or cubed, 1 over just a quantity to the first power is going to use ln. Separating into more than one integral is another trick. So here I have two integrals that are pretty similar looking. X over x squared plus 1, or the reverse of that, x squared plus 1 over x. So one of these is a u substitution and one can be separated. So go ahead and take a second and see if you can figure out which is which. So you'll see the top one is a u substitution. We can let u equal x squared plus 1. So du is 2x, and if I divide by 2, I've got that x dx in the numerator. The second one, though, is not u substitution because the x is in the denominator, and we don't want du in the denominator. But you can separate it. So this is a trick, again, that you'll see sometimes on the AP or sometimes in our homework questions, where it's actually a simple problem, but kind of masquerades as this harder one. So you separate it into different fractions. So I have x squared over x plus 1 over x. Then to solve that, x squared over x is just x. So I simplify that to x. 1 over x, we know the antiderivative of that's going to be ln of x. Okay, u substitution, another common technique you'll see a lot. You want to be looking out for a function and its derivative. Now typically I see students get this correct almost all the time with questions like the first one, where it's pretty obvious, like 2x squared plus 7 in the denominator, 4x in the numerator. It's a real simple u sub. What gets harder is when sometimes the constants don't match up. That can throw you for a loop. Remember, you can always divide or multiply by constants to make it work out. So that's not an actual problem. Trig, again, just sometimes throws us off because we're not thinking about those functions and derivatives all the time. And then ln. So these last two examples, I've got sine squared x cosine x. So everyone's familiar with sine and cosine being derivatives of each other. But sometimes we see sine squared, we go, huh. So here, something like this, you would let me look at the solution one. You would let u equal sine x, not sine squared, because the derivative of u is cosine x. So your problem would end up being u squared du, which is fine. This last one, you'll see lots of variations of ln x over x. Typically use ln x, and then because the derivative of that is 1 over x, that'll be in the problem somewhere. So lots of problems with x and ln x in the same problem will be a u sub, but not all. We'll see that in a minute. So another form that you'll see often is rationals. So when it's rational like this, if it's just 1 over x squared, we can turn that into x to the negative 2 and solve with powers. But if there's anything else going on in the denominator, then we might have to use one of these other types of techniques. So if it's not u substitution, meaning there's no x in the numerator, something like that, you want to think, is it arctan or arcsine? Is it completing the square? Am I going to factor and find the fractions? So those are kind of the types of techniques you'd want to look for. And again, those constants, they can be anything, and you can just pull those outside of the integral. So constants are never a problem, it's just everything else that might be an issue here. So let's look at the solutions. So that first one is just arctan. So arctan you'll see in a lot of different forms. Okay, it has to be some number over x squared plus 1, or some quantity squared plus some constant. So that's where things get tricky. You can have a lot of different quantities in the denominator. The basic form is 1 over x squared plus 1, but you want to kind of check out if there's a squared quantity plus a constant, that can typically be turned into arctan. Second one's an example of completing the square. I have an x squared plus a something x. I can always complete the square in that case because I can add the constant. Same as if the constant is like plus 1 here. Then I can't quite factor it, I could complete the square. So if it's not factorable, you can complete the square. That third option, 3 over x squared plus 6x plus 8, that's a good example of where we can factor the denominator and use partial fractions to find two fractions to integrate. So like here, I could factor that denominator as x plus 4 times x plus 2, and I would kind of put a over x plus 2 plus b over x plus 4 and figure out what those numerators are to finish that off. Now, in the integral chapter, chapter 8, for partial fractions, just to note, we do some harder problems, but the AP exam only tests on linear factors. So you don't typically see quadratic factors on the AP exam. Okay, last technique that we use a bit is integration by parts. Now when you first see integration by parts, it can be a little daunting. Once you learn the technique, it's not too bad. But it can also seem like the hard problems use integration by parts. That's not quite true. Integration by parts are really only used in pretty specific instances. So it can help you to memorize what those instances are, because in general you're not using integration by parts all the time. So it's typically, but not always, a product, like these first three that I've given you. X to some power times sine or cosine, so x cubed times sine x, or x squared times cosine x, anything like that. E to the x times sine or cosine. Okay, this is a special trick you want to learn how to do. Third one, x times ln x. Again, x to any power times natural log here. Okay, so those are kind of the very typical examples. You'll also have things like x e to the x. Again, any power of x here times e to the x. So these are the types of things that you run into, combinations of e to the x sine or cosine, x to a power sine or cosine, x to a power natural log, x to the power e to the x. However, there's two other types of integration by parts problems you want to know about. Or basically one other type, but two examples of that. And that is sometimes there's something like this, where there's no product, it's just ln of x. And what you do is you let u equal ln x, or whatever object here is, and dv equals dx. This works sometimes because some of these functions have derivatives that make this all work out. So this works for ln of x. It works for antiderivative arcsine of x. So functions like that, you're going to find that using this method, integration by parts, is going to work. But in general, it's not going to work for a bunch of other things. So you're really looking at these types of products, and then these kind of special functions like natural log of x or arcsine of x. Okay, so in general, on those other types of things we just saw, you're not going to be thinking it might be integration by parts. You're really looking for products and these types of things. So I hope this has been helpful. Again, as you're doing integral problems, look for patterns and try to really eliminate possibilities so that you can narrow it down to I can only use one or two techniques here, and you can see how to solve it.